Welcome to this coding problem walkthrough. Today, we'll be tackling LeetCode problem number 90, titled Subsets 2. This problem challenges us to generate all unique subsets of a given array, even when the array contains duplicate elements. Let's dive in and explore the approaches to solve this intriguing problem. In this problem, we are tasked with finding all possible subsets, or the power set, of a given integer array nums. What makes this problem unique is that the input array may contain duplicate elements, but the output must ensure there are no duplicate subsets. Importantly, the subsets can be returned in any order, so the focus is on correctness, not the sequence. For the input, we are provided an integer array of length n, and the output will be a list of lists where each sublist represents a unique subset of nums. Let's look at an example. If the input array is 1, 2, 2, the output should include all distinct subsets such as the empty subset, subsets with one element like 1 and 2, subsets with two elements like 1, 2, and 2, 2, and finally a subset with all three elements 1, 2, 2. This demonstrates how duplicate subsets are avoided while generating all possible combinations. Now, let's break down the example further. The input array 1, 2, 2 contains duplicate elements, specifically the two 2's. To generate unique subsets, we consider all combinations but ensure that duplicates like 2, 2 appear only once. For instance, the subsets include the empty set, subsets with individual elements like 1 and 2, combinations of two elements like 1, 2, and 2, 2, and the full combination 1, 2, 2. This guarantees that every subset listed is unique. In another example, with an input of 0, the output is straightforward, the empty subset, and the single element subset, 0. These examples highlight how the solution handles inputs of different lengths and ensures no duplicate subsets are included. In a more complex example, where the input array is 4, 4, 4, 1, 4, we observe multiple duplicate elements, specifically 4 occurrences of the number 4. Here, the unique subsets must account for these duplicates while ensuring no repeated combinations in the result. The subsets include the empty set, single-element subsets like 1 and 4, multi-element subsets like 1, 4, 1, 4, 4, and so on, up to the full combination 1, 4, 4, 4, 4. Additionally, subsets containing only the repeated number 4 are included, such as 4, 4, 4, 4, 4, and 4, 4, 4, 4. This example emphasizes how the solution systematically handles arrays with significant duplication to produce unique subsets. The process of generating unique subsets ensures that no duplicates appear in the output. Let's consider the constraints and edge cases to solidify our understanding. The array length ranges from 1 to 10, and the elements can be any integers between -10 and 10. This means the function must handle small arrays efficiently as well as larger arrays that can produce up to 1024 subsets due to the exponential growth of combinations. For edge cases, if the input is an empty array, the output should simply be representing the empty subset. If all elements are identical, such as 2, 2, 2, the output should only include unique subsets like 2, 2, 2, and 2, 2, 2. Finally, the function must also correctly handle negative numbers. For example, with an input like -1, -1, 2, subsets need to be generated properly while avoiding duplicates. These considerations ensure the solution is robust and handles all possible scenarios effectively. To tackle the problem of generating all unique subsets from an array that may contain duplicates, there are a few approaches we can consider. The first is the brute force approach. This method involves generating all possible subsets, which is essentially the power set of the array, and then filtering out any duplicates. This can be done using techniques like bit masking or recursive backtracking to create the subsets, and then a set or a similar data structure to eliminate any repeated subsets. While this method does work, it's quite inefficient. Generating 2 to the power of n subsets and then spending additional time to check or copy each subset leads to a time complexity of 2 to the power of n*n. Moreover, storing all subsets also requires a significant amount of space, making it 2 to the power of n*n in terms of space complexity. The main drawback is the redundancy in generating duplicates and the extra post-processing step required to remove them, which makes this approach less ideal for the problem at hand. Now, let's explore a more efficient solution, the optimized backtracking approach combined with sorting. By sorting the input array first, we ensure the duplicate elements are placed next to each other, which allows us to skip them during subset generation. The process involves a few key steps. First, we sort the array nums to group identical elements together. Then, we use backtracking to explore all possible subsets recursively. At each step, we make a decision whether to include the current element in the subset. Importantly, to avoid duplicates, we check if the current element is the same as the previous one, and if so, we skip it unless it's part of a new starting point in the recursion. This eliminates the need for post-processing steps to filter duplicates. This approach still has a time complexity of 2 to the power of n*n due to the subset generation, but it avoids redundant computations, making it more efficient. Additionally, it only requires n space for the recursion stack, making it significantly better in handling duplicates directly during subset construction. This method is both elegant and efficient, addressing the problem requirements more directly. Another approach to consider is iterative subset generation. Here, we build subsets one element at a time. Starting with an empty subset, we iterate through each element in the array, adding it to all existing subsets to form new ones. To manage duplicates, we track the subsets generated at the current iteration separately from those carried over from the previous iteration. While this method is viable, it requires careful handling to ensure duplicates are avoided, which can make the implementation more cumbersome. Both the time and space complexity for this approach are 2 to the power of n*n, similar to the previous methods, but the additional complexity in managing subsets makes it less preferred. Given these considerations, the optimized backtracking approach with sorting stands out as the most effective strategy. Sorting simplifies the problem, as adjacent duplicates can be easily skipped, and backtracking offers a clean, recursive way to explore all subsets while avoiding unnecessary computations. The recursive structure aligns naturally with the subset generation process, making it intuitive to implement and efficient in practice. When evaluating the trade-offs, the optimized backtracking approach clearly outperforms the brute force method by eliminating duplicates during the generation process itself, rather than requiring post-processing. Compared to the iterative subset generation method, backtracking is cleaner and more straightforward, especially for handling duplicates. This makes it the preferred choice for solving the problem. The algorithm works as follows. We first sort the array nums to ensure duplicates are adjacent. Then, we use a helper function for backtracking. This function maintains a path list to represent the current subset and adds it to the result during each recursive call. For each element in the array, we recursively decide whether to include it in the subset, skipping duplicates as necessary by checking if it matches the previous element. Finally, the function returns the result containing all unique subsets. This approach adheres to the problem constraints while being efficient, intuitive, and easy to implement, making it the optimal solution for generating unique subsets. In this problem, we aim to generate all unique subsets of an array that may contain duplicates. To ensure the subsets are unique, we need the output to be free of duplicates, and each subset should be sorted internally. A backtracking approach is particularly well suited for this task. By sorting the input array beforehand, duplicate elements are grouped together, making it easier to identify and skip redundant operations during subset generation. For instance, sorting an input like 1, 2, 2 results in 1, 2, 2, which ensures duplicates are adjacent. We'll initialize two key structures, a result list to store all subsets and a temporary list to build subsets during the backtracking process. These steps lay the foundation for our algorithm. The core of the solution lies in defining a recursive backtracking function. This function, backtrack, start, begins exploring subsets from a given index in the array. At each step, we add the current subset to the result list to record it. To generate new subsets, we iterate through the array starting from the current index. If the current element is a duplicate of the previous one and not the first element at this position, we skip it to prevent redundancy. Otherwise, we include the current element in the subset and recursively call the function to explore further combinations. After exploring a path, we remove the last element from the subset to backtrack and try other possibilities. Once all recursive calls are complete, the result list contains all unique subsets. Sorting the array is a critical step for handling duplicates effectively. When duplicates are grouped together, we can easily skip unnecessary work by comparing adjacent indices during backtracking. This ensures that subsets are generated without repetition. Backtracking itself is a powerful approach because it incrementally builds subsets while managing the state of the subset dynamically. The condition to skip duplicates, if I start in nums, I equals nums, I1, reduces redundant recursive calls, which improves efficiency. These insights not only simplify the implementation but also make the algorithm computationally efficient. To implement this algorithm, we rely on three main data structures. First, the subset list is used to construct subsets step by step during recursion. Second, the result list stores all the subsets we generate. Finally, the sorted input array helps us efficiently handle duplicates. In terms of complexity, sorting the array takes O and log n. The backtracking process explores up to 2 to the power of n subsets in the worst case, where n is the length of the array. However, skipping duplicates reduces redundant work, making the process more efficient in practice. The space complexity is O, n, as we maintain the subset list during recursion. This combination of sorting and backtracking ensures an optimized solution. Let's walk through an example to see the algorithm in action. Consider the input array nums equals 1, 2, 2. After sorting, the array remains 1, 2, 2. We start with an empty subset and add it to the result list. Then, we include 1, forming 1, and add it to the result. Next, we include 2, forming 1, 2, and recursively add another 2 to form 1, 2, 2. At this point, we backtrack by removing elements step by step, exploring other possibilities. When we encounter the second 2 at the same level, we skip it to avoid generating duplicate subsets. The final output is 1, 1, 2, 1, 2, 2, 2, 2, 2, which contains all unique subsets. This demonstrates how sorting and duplicate handling ensure correctness and efficiency. Explanation. The provided code is a solution to LeetCode problem number 90, subsets 2, which requires generating all unique subsets of an input array nums that may contain duplicates. Step-by-step explanation. 1. Sorting the input, nums.sort. The input array nums is sorted first to group duplicate elements together. This ensures that we can easily skip over duplicates during the subset generation process. 2. Backtracking framework. A helper function backtrack is defined to build subsets recursively. It takes 2 arguments. Start, the current index in the array from which to begin exploring subsets. Path, a list representing the current subset being constructed. The subsets list is initialized to store all unique subsets. 3. Adding current subset. Inside backtrack, the current subset, path, is appended to the subsets list. Using path ensures we append a copy of the list, not a reference. 4. Iterative exploration. A for loop iterates over indices from start to the end of nums. Duplicate skipping. If the current index I is greater than start and the current number nums, I, is the same as the previous number nums, I1, we skip this iteration to avoid duplicate subsets. Otherwise, the current number nums, I, is added to the path, and backtrack is called recursively with the next index, I plus 1. 5. Backtracking step. After the recursive call completes, the last element is removed from path using path.pop. This step ensures that the algorithm can explore alternative subsets by backtracking to previous states. 6. Returning the result. After exploring all possible subsets, the function returns the subsets list. Complexity analysis. Time complexity. Sorting the array takes O and log n. The backtracking process generates all subsets, which is O, 2 to the power of n, for an array of size n. Thus, the overall complexity is O, n log n plus 2 to the power of n. Space complexity. The path list and recursion stack require O, n, space. This approach ensures that all subsets are generated without duplicates, leveraging sorting and efficient backtracking. This is the Java implementation of the subsets 2 problem. It mirrors the Python logic by using backtracking to generate all subsets while avoiding duplicates by sorting the input array and skipping repeated elements during recursion. Key differences include explicit type declarations, use of Java's list and ArrayList for collections, and the arrays.sort method for sorting the input array. The problem subsets 2 challenges us to find all possible subsets of a given list of integers while ensuring that these subsets are unique, even when the input list contains duplicates. To handle duplicates effectively, we first pre-process the input by sorting the array, which helps group identical numbers together. For example, if the input is nums equals 1, 2, 2, sorting gives us nums equals 1, 2, 2. Next, we employ a recursive backtracking approach to systematically explore all subset possibilities. We initialize an empty list called subsets to store the results and start with a helper function backtrack, beginning at index 0 with an empty path. At each step, we add the current path to the list of subsets. For instance, starting with the empty path, we add it to subsets, resulting in subsets equals. Then, we iterate over the array, appending one element at a time to the current path. For example, when we append nums 0 equals 1, the path becomes 1, and we add it to subsets, giving us subsets equals 1. Continuing, we append nums 1 equals 2 to the path, resulting in 1, 2, and add it to subsets, making it subsets equals 1, 1, 2. Next, we append nums 2 equals 2 to the path, resulting in 1, 2, 2, and add it to subsets, giving us subsets equals 1, 1, 2, 1, 2, 2. To avoid duplicates, we skip over any repeated values after processing them. For instance, after backtracking to 1, 2, we skip the second occurrence of nums 2 equals 2 because it has already been processed in this context. After backtracking further to 1, we append nums 2 equals 2 again, generating the path 1, 2, which is added to subsets as a unique subset, making it subsets equals 1, 1, 2, 1, 2, 2, 1, 2. Subsequently, we backtrack completely to the empty path, and continue by appending nums 1 equals 2. This creates the path 2, which is added to subsets, resulting in subsets equals 1, 1, 2, 1, 2, 2, 1, 2, 2. Following the same logic, appending the next nums 2 equals 2 gives the path 2, 2, which is added to subsets, producing subsets equals 1, 1, 2, 1, 2, 2, 1, 2, 2, 2, 2. Skipping duplicates ensures that no redundant subsets are included. For another example, consider nums equals 4, 4, 4, 1, 4. Sorting this array gives nums equals 1, 4, 4, 4, 4. Using the same backtracking strategy, we generate subsets by appending elements to the path while skipping consecutive duplicates. This process yields unique subsets like 1, 1, 4, 1, 4, 4, 4, 4, 4. As a result, the final output for example 1 is subsets equals 1, 1, 2, 1, 2, 2, 2, 2, 2, and for example 2, it is subsets equals 1, 1, 4, 1, 4, 4, 1, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4. This ensures that all subsets are unique, even when duplicates are present in the input. To analyze the time complexity of this algorithm, we start with the sorting step. Sorting the input array ensures that duplicate elements are adjacent, and this operation takes n log n, where n is the number of elements in the array. Next, we move to the backtracking process, which is responsible for generating all possible subsets. In the worst case, when there are no duplicates, there are 2 to the power of n subsets since each element can either be included in or excluded from a subset. For arrays with duplicates, the algorithm avoids generating duplicate subsets by skipping over adjacent duplicates. However, in terms of big O complexity, we still consider the worst-case scenario where 2 to the power of n subsets are generated. Additionally, for each subset, the algorithm makes a copy of the current subset, which takes k time where k is the length of the subset. In the worst case, the sum of all copying operations across subsets is n asterisk 2 to the power of n. Combining these steps, sorting contributes n log n, and the backtracking process dominates with n asterisk 2 to the power of n, leading to an overall time complexity of n log n plus n times 2 to the power of n. This overall time complexity of n log n plus n times 2 to the power of n simplifies to n asterisk 2 to the power of n in the asymptotic sense, as the backtracking process dominates for large input sizes. Now, let's examine the space complexity. The first component is the space required for the recursive call stack. Since the maximum depth of the recursion tree is n, the stack requires n space. Next, the path list, which stores the current subset being constructed, has a maximum size of n. However, this space is reused across recursive calls and does not contribute to additional memory. Finally, we consider the output list subsets, which stores all the unique subsets. In the worst case, there are 2 to the power of n subsets, each with up to n elements, requiring n asterisk 2 to the power of n space. Combining these, the overall space complexity is n asterisk 2 to the power of n, dominated by the storage of subsets. The total space complexity of the algorithm is n asterisk 2 to the power of n, which includes n asterisk 2 to the power of n, for storing the subsets in n, for the recursion stack. Let's compare this optimized approach with a brute force method. In a brute force approach, all 2 to the power of n subsets would be generated first, without considering duplicates, and a set or hash table would then be used to filter out duplicates. This results in a generation cost of n asterisk 2 to the power of n, and an additional filtering cost of 2 to the power of n asterisk n. The space complexity in this case is also n asterisk 2 to the power of n, as all subsets are stored before filtering. On the other hand, the backtracking algorithm integrates a duplicate check during subset generation using the condition if I start in nums, I equals nums, id1, continue. This avoids generating duplicate subsets and eliminates the need for post-processing, making it more efficient in practice, even though the asymptotic complexity remains the same. To understand why the time complexity is n asterisk 2 to the power of n, let's consider the structure of the backtracking algorithm. The recursion generates nodes in a tree, where each level corresponds to a decision of including or excluding an element. For n elements, the total number of nodes in this tree is 2 to the power of n. At each node, a copy of the current subset is made, which takes n in the worst case. Summing this cost across all nodes gives n asterisk 2 to the power of n. Sorting the array at the start adds n log n, but for large n, this step is dominated by the cost of generating subsets. Thus, the overall time complexity is n asterisk 2 to the power of n. Similarly, the space complexity is n asterisk 2 to the power of n, with n asterisk 2 to the power of n, for storing the subsets in n, for the recursion stack. This analysis confirms that both time and space complexities are dominated by the exponential growth in the number of subsets as n increases. When solving subsets too, there are a few common mistakes to watch out for. First, failing to sort the input array can lead to duplicate subsets because duplicates won't be grouped together. Sorting ensures that you can handle duplicates effectively during backtracking. Next, it's essential to skip over duplicate elements in the recursive process. If you don't, you'll end up including redundant subsets. To manage this, check if the current number is the same as the previous one, and only process the first occurrence at each recursion level. Another common issue is an incorrect base case in your recursion. If you forget to add the current subset to the results or mishandle the stopping condition, your solution may be incomplete. Finally, always ensure proper backtracking by undoing changes to your subset state after recursion. If you modify the subset but fail to revert it, your results will be incorrect. These mistakes are easy to avoid with careful attention to detail during implementation. Additionally, using inefficient data structures can slow down your solution. For instance, if you rely on sets to store subsets and then convert them back to lists, you'll introduce unnecessary overhead. Stick to list-based operations and ensure uniqueness through recursion logic instead. From an interview perspective, sorting the array is a critical step. Interviewers often want to see if you recognize its importance for handling duplicates. This problem is also a classic example of backtracking, so be prepared to discuss recursion, state management, and how you prune unnecessary branches. Don't forget to explain the time complexity of your solution. Generating all subsets has an inherent complexity of 2 to the power of n, but sorting adds an additional n log n, so your explanation should account for both. Lastly, always address edge cases, such as empty arrays, arrays with all identical elements, or those with no duplicates. These discussions demonstrate a thorough understanding of the problem. This problem connects closely to several related problems. For example, LeetCode 78, subsets, is a simpler version of this problem where the array contains no duplicate elements. It's a good starting point to understand the core recursion logic. Another related problem is LeetCode 47, permutations 2, where you need to generate all unique permutations of an array that includes duplicates. The duplicate handling logic is very similar to what we use here. LeetCode 40, combination sum 2, is another close variation, where you find unique combinations that sum to a target, also requiring careful duplicate management. Lastly, LeetCode 39, combination sum, removes the duplicate constraint entirely, making it a helpful comparison point for understanding how handling duplicates changes the approach. Exploring these problems can deepen your understanding of recursion and backtracking in different contexts. Now, let's look at some alternative approaches to solving subsets too. One option is iterative subset construction. This method starts with an empty subset and iteratively adds each element to existing subsets. While simpler to implement, it often relies on a set to filter duplicates, which can slow things down and use more memory. Another approach is bit masking, where you use binary numbers to represent whether an element is included or excluded from a subset. While this avoids recursion, handling duplicates efficiently becomes more complex, and it can be less intuitive for interviewers. Finally, you can use a hash set to store subsets as tuples, which automatically handles duplicates. Once you've built the set, you can convert it back to a list. However, this method typically consumes more memory compared to backtracking. Each of these approaches has trade-offs in terms of implementation complexity, performance, and intuitiveness, so it's important to choose the one that best fits the problem constraints and your comfort level. Great job following along. To recap, we explored how to generate unique subsets using backtracking and tackled the challenges of handling duplicates. Remember to practice similar problems to sharpen your skills. Thank you for watching, and don't forget to like, comment, and subscribe for more. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!